What do you think of when you think of artificial intelligence? Do you think of futuristic robots? Terminators that might take over the planet? A disembodied intelligence that someone could fall in love with? We're still a long ways off from these kinds of artificial intelligence, and hopefully the Terminator variety is never unleashed. But in lots of other ways, AI is already here and making incredibly rapid advances in many, many domains. There is AI in the little robot that zooms around cleaning your floors, AI in your phone recognizing your face and your voice. AI is deciding what you see on your social media newsfeed and what recommendations you're given about the next video or TV series or new music release to enjoy. Maybe you're driving a car with driver assist powered by AI as we wait for autonomous vehicles and drones to move from pilot programs to widespread use. Or relying on AI to adjust the thermostat at home. AI is producing many of the great effects we can now get with our smartphone cameras and is responsible for many of the features we've grown used to in video conferencing, like virtual backgrounds or automatic highlighting of a speaker, not to mention smoothing out internet hiccups and giving you the option of wacky special effects. AI is powering the apps we use to decide what route to take home or order a meal, groceries, or a ride, deciding what options we see, what prices we're offered, and how fast the service will be. And it's not just consumers that are using AI daily. Banks and financial institutions are using AI to detect fraud and money laundering and to score loan applicants. Many businesses use AI-powered chatbots to support customer service. Online retailers use AI to decide what products to show. AI is helping to coordinate shipping and delivery logistics, automate payments, monitor employees, review job applications and schedule interviews, read, sort, and respond to emails, contracts, and other documents. Much more is on the near horizon. AI systems can already diagnose some diseases faster and more reliably than human doctors, and more robust systems are in development to monitor patients and recommend optimal treatment strategies to improve healthcare. Cities are exploring the use of AI to make buildings, transit systems, and public services smarter. Schools and colleges and universities are looking to AI to improve education with smart tutoring and evaluate applications. Some places are trying out AI to help identify children at risk for elevated lead levels, or pregnant women at risk for birth complications, or buildings at risk for housing code violations, so that those at risk can be prioritized for community resources and support. At least one large city is experimenting with AI to help leverage homeless youth social networks by identifying peer leaders who can be most effective in getting the word out about health-related information, such as how to avoid the spread of HIV. AI could help us improve security at the border, track climate change, invent new drugs and materials, and adjudicate claims in everything from tax to immigration to Social Security. AI could transform our courts and dispute resolution processes, and how we design public policy and conduct elections. The possible transformations coming from AI are truly astonishing, and they present most of us who are not computer scientists, and even some computer scientists, with a challenge. This is new technology, and in many ways it's not like anything we've seen before. And it presents both opportunities and risks that we haven't really addressed before. So one of the things I've learned from talking with people in industry and governments and civil society organizations is that it helps to understand a bit just how AI works, what's under the hood. And that's what I'm going to focus on in this talk. Let's start with something that is familiar, computer programming. Now, even if you are not a programmer, even if, like me, you cannot write computer code, you probably have a good intuitive understanding about how computers work. When we program a computer, we, the humans, tell the computer exactly what to do with data we give it. The software inside your word processing program says things like, if the Shift key is pressed, make the next letter that is pressed on the keyboard a capital. Or, compare each word in this document to a list of properly spelled words in this list. And if there's no match, put a red line under the word on the screen. Generically, that's all a computer program is, a collection of rules for the computer to follow. If-then statements, if shift key, then capital, if misspelling, then red line, if X, then Y. Up until now, this is how all of even the most amazing and powerful computer programming, the stuff that does things like keep planes in the air, has worked. Somebody told the computer what to look for and what to do with what it found. And even if the code took thousands of lines to write, every line was written by a human, and a programmer could always read the code and see, there, that's where I told the machine to do Y when it saw X in the data. Now think about what that means for how we use computers. We want to do something like find all the people in this city who haven't been vaccinated and put them on a priority list for a reach out from public health. So we program, or more likely we ask someone else to program, a computer to review a data set composed of vaccination records and produce a list, or better yet, schedule a visit for a public health worker when they are next in the neighborhood. We are fully in control. It's fairly easy for us to understand what the computer is doing. And if something goes wrong, if there are objections that giving the computer the list of people who have been vaccinated is a violation of privacy, or if the scheduled visits for public health workers are biased against some neighborhoods, or if they violate employment rules, well, we know who to talk to. We know who is responsible. The person who told the computer, or the programmer, to tell the computer what to do. And it's reasonable to hold that person or department responsible, because we're not asking for them to do something unreasonable when we ask them to take care in what they ask the computer to do. Some sets of instructions for computers might be really complicated, like the programs that help planes fly on autopilot. But at some point, these complicated instructions were developed by human experts, aerospace engineers, perhaps. And they were tested by other experts to make sure they behaved like everyone expected them to. Accidents can happen, but the risk is mostly known and manageable. And this is what modern AI is changing. The AI that is transforming almost everything we do writes its own rules. It accomplishes some pretty amazing feats by doing so, but it also means that we don't have the same kind of control over it that we have over conventional programming. It is not easy to understand why the AI is doing what it's doing. And it is much more challenging to figure out how to hold humans responsible for what the AI does. That's why figuring out how to use AI in government and how to regulate its use in industry and civil society is such a new challenge. You might be thinking, well, why build or use AI that you can't easily control and understand? Why not stick with AI based on rules written by humans? That is, in fact, how the early efforts to build artificial intelligence back in the 1950s started. Computer scientists tried to write out all the rules for how a computer should solve a problem, like how to drive a car or play chess. And there were some important breakthroughs with this kind of AI, sometimes called good old-fashioned AI or GoFi. This is the kind of AI that was inside IBM's Deep Blue machine, which beat Garry Kasparov, the world champion at chess, in 1997. But it eventually became clear that the world is just too complicated to write down all the rules, and progress in AI was very slow. Until 2012, when the age-old strategy of sidestepping an obstacle yielded a new solution. Don't try to write down the rules. See if the machine can figure out the rules. That's what the modern approach to AI, known as machine learning, does. Instead of a human telling the machine what to do, humans give the machine lots of data about the task that they want the machine to do, the goal they'd like the machine to achieve. And then they program the machine to crunch all that data to figure out what rules would work best to get another machine or program to achieve the goal. So instead of giving the machine a rule like, if a person is missing from the list of vaccinated people, put them on a priority list for public health to reach out, we give the machine lots of what we call training data. Vaccination rates, infection rates, demographics, medical services, online searches, travel patterns, you name it. This is historical data, data from the past. And then we ask the machine, what rule for public health priorities would have achieved our goal of reduced infection rates in this historical data? The machine decides what if X then Y rules it would have been best to use. So how does it do this? Basically, through trial and error. It starts with a random guess, like online searches for cough medicine are good predictors of illness. Then it sees how well a model built with that guess does at predicting the thing we told the machine to care about, infection rates. Of course, it does terribly at first. So it adjusts the model. It tunes the dials. Let's put a little more weight on data from medical records about underlying risk factors in the community, such as diabetes. Maybe that does a little better. How about some weight on how much people in this neighborhood use public transit? It's like experimenting with recipes in your kitchen. A little more salt? Oh no, less salt. The machine just keeps doing that, tuning the model millions of times over and over until, if we've got good enough training data, it gets pretty good at predicting the thing we asked it to. Then we can use the model that the machine learning system built by getting good at predicting the training data by giving it the real-world data, the new data we want to make choices about. So we could give our public health model current data about infection rates, vaccination, public transit, online searches, etc., and ask it to recommend what we should do, where to send the public health resources. Give it the X's and let it tell us the Y's based on the rules it built up. If we think it's really good, we could even convert that recommendation into an automated decision, straight from the mouth of the machine learning model to the ear of the public health worker's daily schedule. Sometimes machine learning looks like it's doing magic because it starts seeing things, patterns in data that we humans did not see or know about. And that's precisely why it was so hard for us to write down all the rules. We didn't know already that there is a hidden relationship between public transit use and infection rates, or maybe only in some neighborhoods, only at times when the buses get more crowded. When IBM's Deep Blue beat Garry Kasparov using good old-fashioned AI, every move the machine made had been thought out at some point by a human. That's where the rules the machine used came from. But when Google's DeepMind built AlphaGo, a machine learning-based computer program to play the ancient game of Go, and sent it up against the world champion Lee Sedol in 2016, well, the machine surprised everyone. It made moves, brilliant moves, that no human had ever imagined. But just a game, right? Well, in 2020, DeepMind's AlphaFold, built using the same AI technology as AlphaGo, achieved a major scientific breakthrough, discovering the secret to predicting the 3D structure of proteins, a challenge that human biologists had been working 50 years to solve and weren't sure they ever would. As one evolutionary biologist put it, this will change medicine. It will change research. It will change bioengineering. It will change everything. So, we face this trade-off with AI. It can do things we never dreamed of and potentially bring us enormous benefits. But it does so precisely by doing things we don't predict or understand. So that's now our challenge. How do we make sure that this powerful technology does not do more harm than good. So let's look a bit at the pipeline that produces AI and where the choices are being made that influence the way AI works and the balance of benefits and costs it produces. From 30,000 feet, it looks something like this. A computer takes in training data and applies machine learning algorithms, which are rules for figuring out the best rules. And through millions of iterations, produces a model, a set of if X, then Y statements. The model is then deployed, given current data to make real predictions and recommendations or decisions. Some people think the pipeline starts with the training data, but I think we have to go one step back to the decision to build AI for a particular purpose in the first place. Who makes that decision? What AI is being built? This is a critical place for people in policy and government and civil society to get involved. Right now, most of the AI being produced is being built in response to commercial incentives, market demand, inside big tech companies. And that's why a huge amount of our current AI is focused on building better techniques for targeted advertising, because that's the business model for monetizing a lot of the digital economy. Now, I'm an economist. I like markets, and I recognize that better advertising can mean better goods and services and more consumer surplus. But it's become a crazy powerful driver of some not so great stuff, using those same AI technologies to target political messages and spread conspiracy theories and misinformation, for example. Figuring out how to get people addicted to their phones and screens to just keep scrolling. But if AI is going to help us solve real human problems, improving government services, making our legal and administrative systems fairer and more accessible, making our communities healthier and safer and our planet more sustainable, then we have to start paying attention to the very first step in this pipeline. We need more AI being built to the specs of the public sector, not just the private sector. For governments, that means some combination of public investment, AI policy, AI procurement policy, and the types of public-private sector partnerships we use to build public infrastructure. We'll need to get creative to make sure the AI we get is the AI we need. Now, let's look at the choices to be made about data. First, there is the data used to build the AI. Suppose we want to build AI to make better predictions about mortality risk in ICUs to help healthcare personnel and hospitals make better decisions. A good starting point is data from electronic health records. So perhaps we get a large hospital or healthcare system or insurance company to share those records with our AI developer team, and we ask the team to build a model that can predict mortality events, death in or just after the ICU visit, which is an entry in the electronic health record using all the other information in a patient's health record. This data will get divided into 3 sets. The first and biggest set is the training set. The information in that set about death events is the output variable that the AI model is going to try to predict using all the other information in the set as input variables. The second data set is the validation set. This is the data used to check to see how well the guessing is going as the model trains. The errors made by the current version of the model in predicting mortality in the validation set tell the AI developers that they need to keep tuning the dials, aiming to bring the error rate down. The third set is the test set. This is where the AI developers check what they think is the final model. They don't go back and tune the model after they see those results, because that would be cheating. We want the performance of the model, the error rate in predicting mortality, that's revealed by running the model on the test set to be a good guide to what is going to happen when we start using the model on new, unseen data out there in the real world. Now, I've told you a lot about data, probably more than you wanted to know. But the key thing I want you to see is that there are a lot of decisions being made here about what data to use and how to use it. And those are decisions that lots of people other than just the computer scientists need to be involved in. How is a data set being constructed? What's in the electronic health record? What's not in the electronic health record? Who's in the data set? Who is left out? If we train the model on data from a wealthy suburban hospital, it might not perform very well for populations in rural or diverse urban communities. If the data sets are too small or too narrow because of barriers to data sharing put in place by hospitals trying to protect trade secrets or lawyers worried about liability or privacy oversight, then they might be missing important variables, or they just might not be rich enough to yield good insights. And what about those test sets? Who is deciding what is an adequately representative data set? Who is making sure there was no cheating during developing? Who is testing to make sure that the performance on the test set is not a fluke? These are all questions that we should not be leaving to computer scientists alone. They are ones that policymakers need to be answering. Once we have a model that is performing well at prediction, we still have a lot of choices to make about if, where, and how the model should be deployed. Who will decide if an AI system is fit for purpose, safe enough, and fair enough to be used? How will they decide that? What will be the relationship between the AI system and the humans? Will the AI system be limited to making recommendations for humans to make decisions? Or will it become an automated decision system? How will humans check to make sure it is working as expected and intended? Will humans overtrust the machine's recommendations? Not trust them enough? If the AI-based system makes a mistake and causes harm, will we know? Who will be held accountable? Will our systems of accountability and responsibility work when the humans using the machine or judging fault don't really understand how it works? These are really hard questions. They are ones that I firmly believe there are answers to, but we need to get cracking on the research and policy making needed to get those answers. Today, we are living in almost a complete regulatory vacuum around the development and deployment of AI. It's happening so fast, and it's a critical reason why governments and policymakers need to get their heads around AI and step up to the plate. Just think about that AI helping to reduce mortality in healthcare. Almost everyone who works in healthcare is licensed in some way. Everyone except the AI developers building AI systems. And every drug and medical device in use has been tested and certified by independent companies and agencies with expertise in testing and certification. But we don't have any of those systems in place for AI yet. It's easy to think the answer is for governments to hold up a big stop sign and just ban AI. But there are at least 3 big problems with that. First, we'd be forgoing all the benefits AI can bring us. A bit like saying no to the Industrial Revolution 200 years ago. Our economies work pretty well today, but there are still billions around the globe living in poverty. We are facing enormous challenges to health, sustainability, human rights, and peaceful societies. AI won't solve all our problems, but it can definitely help. Think about what's possible when AI can help diagnose illness in remote communities and track water quality better than we can now. Second, there's really no way to just stop AI because it's far from easy to draw the line between what is and what is not a use of AI. Suppose we wanted to say, as legislation around the globe is now trying to do, that governments should not use automated decision-making. Governments already use loads of automated decision-making. An algorithm is just a rule for how to respond to data. A risk scoring system that tells people in a government department how to decide who gets a small business loan or who is released on parole is an algorithm. And it might be an automated decision-making system. Is it better or worse if that system is built on eyeballing the data, doing conventional data analysis of the data, or using machine learning? And third, there's really no way to stop industry from using AI. AI is what we economists call a general purpose technology. It can help us do just about anything. In fact, lots of people don't even like to think of it as a technology because it's not embodied in a product or a machine per se. It's an approach to solving problems. It's a way of understanding data. Industry will keep building AI, and it won't be possible to make them stop. Governments can ban particular uses of data, like the use of facial recognition software by police or retailers, but it will be almost impossible to keep up with all of the possible uses of this way of analyzing the world. So back to our core question. How do we make sure that this powerful technology does not do more harm than good? Answering that question will require new thinking, not only from computer scientists, but also from social scientists and humanists and policymakers. In fact, it's critical for those of us who are not computer scientists to understand and be involved now in how AI is being built and regulated. The raw technology may be hard to predict, but that doesn't mean that this is how it gets used or deployed in the world. We have to remain in charge. The biology of complicated drugs, like mRNA vaccines, is hard to predict. But that means we design effective ways of testing drugs and require testing before we send them out for people to put into their bodies. The challenge in deciding when it is smart to use AI and how best to build and regulate it is a daunting one. But it is one we can and must respond to. We all have to be involved. We all have to understand better what AI is and how it works. Computer scientists are good at what they do, but not at what the rest of us do. We need to be working together to make AI that benefits us all.